This video is going to have a look at structural isomerism and isomers, so the kinds of isomers that you come across in your first year of A-level chemistry. So isomerism is actually quite a large field. Structural isomers are something that we come across actually probably sometimes at GCSE, early on in A-level, because alkanes have structural isomers. And then there's this group we call stereoisomers. So the word stereo means two or a pair. And so when we are thinking about stereoisomerism, we're talking about things where there are only two options. And the main bit of stereoisomerism that we've done at A-level is our cis-trans or EZ. You will also, in the second year of A-level, if you haven't done it already, look at enantiomers, which arise from having 4 different groups around 1 carbon. At A-level, we wouldn't look at conformers or rotamers. These are more complicated isomers caused by having a ring or some other structure that cannot rotate. But the idea then of structural isomers, there are lots and lots of options for structural isomers. The bigger the molecule gets, the more options you have of branching, positioning, whereas cis-trans, there are only 2 options of each type of either cis or trans. So structural isomers, if I was to take a molecular formula, C5H12O, then what sorts of isomerism could we have within this banner of structural isomers? So the way that the atoms are arranged is different, but the molecular formula would be the same. Well, one thing that we could have is we could of course introduce branching of the carbon skeleton, and all of these structural isomers would be ones we'd be expected to be able to name. So let's have a go at naming the ones we've got here. The one at the top is nice and easy, so there are 5 carbons in the chain, and then the OH group is on the first carbon because we take the smallest number, so that would simply be called pentan-1-ol. That would be probably the simplest version of this formula that we could write. And then the next one down, this time we've got 4 carbons in the main chain. The OH is still on the first carbon, and there is a methyl group which is on carbon number 2. So we would call this one 2-methyl, and now because it's 4 carbons in the main chain, it's butan, and it's still 1-ol. And then one underneath is just more branching going on. The longest chain of carbons we have is 3, and don't forget to check in the other direction. It's the same in the other direction, so it's still 3. So we're going to have propan. The OH is still on the first carbon, so we still have propan-1-ol. And then on the second carbon in, there are 2 methyl groups. To represent the 2, we used di. So di is for the number of different groups, and then numbers such as 1, 2, etc. are for the positioning. So we still need the positioning. We would call it 2, 2. In this instance, perhaps the 2 isn't quite so necessary, because if we've only got 3 carbons in a row, then in order to add a methyl group, it has to go on the second carbon. If it went anywhere else, it would be extending the carbon chain, and we'd be back to butan instead of propan. So these ones, what's important to note here is that the carbon structure is changing, but the actual OH group is in the same position. And the reason that's important is because if you were trying to work out oxidation reactions of these alcohols, they are all still primary alcohols. And so we haven't changed the types of chemical reactions that these would undergo. There would be changes to their boiling point because they've got different surface area. So if I was instead to look at the same formula, so still C5H12O, then Another way of having a structural isomer would be simply to move the position of the OH group. And so the first one, we'd be looking at pentan 1-ol. The second would be pentan 2-ol. And the third would be pentan 3-ol. When it comes to naming, obviously that would be the only ones that you could have with a straight chain of 5. Any more isomers, if you move the OH to the next carbon along, it would be back on the second carbon. Do be careful, pentan 1-ol is a primary alcohol because the OH group is attached to a carbon with 2 other hydrogens and only 1 other carbon. Pentan 2-ol is a secondary alcohol, but don't leap to conclusions because pentan 3-ol is also a secondary alcohol. So there's still only 2 carbons attached to the carbon with the OH group. It doesn't have another carbon, so it still has a hydrogen that can be removed. It can still be oxidized. The only way that you could make a tertiary alcohol is if you took one of the branched isomers from the previous page and then moved one of the OH groups to where there was a branching, so that you would have 3 carbons and an OH group from the same carbon. And then finally we could go even more extreme. So we've seen how primary and secondary and tertiary alcohols can be isomers of each other and they will have different chemical reactions. Well, even more than this, we could in fact have an isomer which is entirely different functional group. So these 2 molecules are not alcohols. You may have seen them, you may not. They're known as ethers. They are very rarely talked about in A-level chemistry. You wouldn't have to worry about naming them. If you were, for example, the top one would be called ethyl propyl ether because there's an ethyl group and a propyl group, and the ether is the single bond O in the middle. Or there's methyl butyl ether underneath. They're just very volatile chemicals. We don't do a lot about their reactivity or anything else. One thing that you will come across though, which is much more commonly talked about, is when you look at carboxylic acids in a little bit more detail. So this molecule, for example, is propanoic acid, 3 carbons with a carboxylic acid group at the end. Carboxylic acids are isomers of esters. And so that would come up in spectroscopy questions about chemical tests, where, for example, you've worked out the molecular formula and you're now trying to work out what the actual molecule is. So just something to be aware of with structural isomers, that you can have completely different functional groups that still have the same molecular formula. So EZ isomerism. EZ isomerism is something that applies specifically to alkenes, and in a little while we'll also talk about why it's sometimes called cis-trans and what the difference is there. First, we're just going to look at what it is, how it arises, and what you need for EZ isomerism to arise. So the molecule on the left is ethane, and the molecule on the right is ethene, and the green shading there is to represent the electron density of this pi bond. So remember, when we have a single bond, the electrons are directly in between the atoms, as they are between the carbon and the hydrogens, and between the 2 carbons in ethane. And whereas once that's happened, you can't put another pair of electrons between these 2 atoms, and this is why the pi bond arises from overlap of p orbitals. So what that means is that there is free rotation around ethane. So any of these hydrogens can move and be opposite any of the other hydrogens, and in fact that movement is happening all the time. So these atoms are completely switching places all the time. That can't happen in a molecule of ethene. So this hydrogen cannot flip and end up over there independently of these two. So the only thing I can do with ethene is rotate the entire molecule. So this group will always be opposite this group unless I break bonds and make a new molecule, which is what isomerism is all about. So the first thing that you need for EZ isomerism is there is no free rotation around the carbon-carbon bond. You can also see this type of isomerism in a ring structure, because there's no rotation in a ring either, because the atoms are held in place by the rest of the ring. But we have no free rotation around the CC bond, but ethene doesn't have isomers, and that is because ethene has only got hydrogens attached to each carbon. So if I were to label each of these atoms A and B and C and D, what's important is that A and B are not the same and that C and D are not the same. B and C can be the same as each other, and A and D can be the same as each other, because what we're looking at is we need to have two different groups on each carbon in the double bond. And we'll look at why that is when we look at some examples. So the nastiest thing that they ever do is obviously give you these lengthy molecular structures, and you have to work out whether they've got EZ isomers. So you've got to find the double bond in these structures and then work out what's attached either side. So looking at my first one, the double bond is in the middle, and I can spot that because instead of CH2 I've got CH. But I could draw it out anyway. I'm not going to draw the whole thing. I'm just going to draw. There's a C. I'm going to separate that H out so I can clearly see what's attached. I'm going to separate that H out, and there's a CH3. And now what I'm going to do is see that these carbons in the middle have 3 bonds. That's how I know the double bond is there, because CH3 clearly has already got 3 things attached and then another bond. So that's where my double bond is. And then I look at each carbon atom. So the one on the left has got a hydrogen and a CH3. So that has 2 different groups. The one on the right, the same. So it also has 2 different groups. So this does have EZ isomerism. Now the way you've drawn it there, you can't see that it has EZ isomerism, and that is because I've not drawn it showing the shape. I've shown a 90-degree angle instead of 120. In the next bit, when we actually assign EZ isomerism, we will look at how to draw them a little bit better than this. At the moment, I'm just deciding, does it have 2 different groups on a double bond? So the next one, going from that structural formula, 2 lots of CH3, so they must both be attached to that C, because CH3s have to go on the end. So I'm going to need to draw a carbon with 2 CH3 groups on it. The next thing is a Br, so that must be attached to that carbon as well. So that carbon's got 3 things attached to it. It's not part of the double bond. The next carbon though says C and then H. And then the next carbon has 2 hydrogens, which means looking at these 2 carbons on the right, I can see they don't have enough bonds around them, and that must be where my double bond is in the molecule. So now I'm going to look just at the carbons in the double bond. Here's the first one. Does it have 2 different groups? Yes, it's got a hydrogen and then it's got a carbon with all sorts of things attached to it. But the one on the right doesn't. So the one on the right has 2 hydrogens. What that means is, if I were to break these 2 bonds and swap these 2 atoms round, I still wouldn't have a different molecule, because I could do that just by flipping the molecule over. That's why it doesn't have EZ isomers. Third example, So this one, again, I've got two CH3s joined to a C with an H attached. So there's my H, there's my CH3, there's my CH3. The next thing I've got, so I've done those bits, this is another way of working with structural formula, is a C with just an H. So I'm now going to tick that one off. And then the next thing I have is a C and an H with a BR attached as well. So I have an H and I have a BR. So double bond needs to go between those two. And then I can look at the two carbons in the double bond. So the one on the left has a hydrogen and a carbon with methyl groups attached. Those two are different. The one on the right has a hydrogen and a BR. So those two are different as well, which means that both my carbons have different groups. So that does have EZ isomerism.